Action. Just kidding. So we're going to talk about momentum, and specifically linear momentum. Momentum is the product. Wow, I'm just forgetting all of my words here. Momentum is the product of your mass and velocity. So that means we have to take into account both mass and velocity when it comes to momentum. And then velocity here plays a super important role because velocity, remember, is both speed and direction. In order for it to be a velocity, we have to have a magnitude of how fast it's going and what direction it is going in. So with that being said, this direction part is super important because it relates to momentum. Momentum, because of this, is a vector quantity. Right? It has a magnitude and a direction. And the direction heavily affects our momentums whenever we calculate them. So the equation we get for this, momentum is measured as a lowercase, we use a lowercase p for it, and it is equal to mass times velocity. The units for these bad boys are kilograms, as always, for mass, MKS. And then for velocity, we use meters per second. The product of those two together doesn't give us anything fancy, it just gives us literally kilogram meters per second. Now, when we look at this, we can have two different objects that have the exact same momentum because there are two different variables in play here. We can have a bigger object at a lower speed or a smaller object at a higher speed, and those two can have the same momentum. An example would be if I had let's say a car. So we have a car going. It's going to be a terrible car, I apologize. Oh, no wheel wells. Wheel. This will be the front of the car. Bam, he's driving backwards for once. That way. So the car weighs 2,000 kilograms. It's an extremely heavy car. And it is traveling at 10 meters per second. If we take these two together, we multiply our mass times the velocity, we would get a momentum of 20,000 kilogram meters per second. Now, I could have something else traveling with the exact same momentum, even if it's much smaller. So if, let's say, for example, we had a bullet. It's a very sharp bullet. It is traveling in a direction. It's going to be traveling in the same direction as our car. It only weighs, let's say it's a big bullet, like a 50 caliber round or something. Let's give it a different mass. Let's say 1 kilogram just for the sake of easy numbers. A 1 kilogram bullet, insanely large. We have no idea how fast it's going. It is blank meters per second. But we know that it has the same momentum, 20,000 kilogram meters per second. So therefore, that gives us an information we could solve to see how fast it would have to go to have the same momentum as our car. In solving for that, we know that momentum is equal to mass times velocity. So if we're looking for velocity, we would divide by momentum or mass on both sides. So momentum divided by mass is equal to velocity. So 20,000 divided by 1 gives us 20,000 meters per second, which is too fast to be realistic. That would be roughly about 40,000 miles an hour, and that is just excessive. Fun. Now, in that little example, I had to point out the fact and make sure that we realized that the bullet was going in the same direction in order to have the same momentum. And the reason for that is because the sign is super important. Sign is super important. Because the sign tells us what? It tells us the, don't answer that question, it was rhetorical. The sign tells us the direction. So if I tell you that you have a momentum of positive 20 kilogram meters per second, that means that I have a momentum in the positive direction, which we typically assume as to the right. So in this direction. Now, if we have a different momentum that adds up, let's say we had two objects that were going in separate directions, and then they stick together, then we have a separate momentum that is going, so we'll say momentum 1, momentum 2 is negative 40 kilogram meters per second. This would mean that we have a momentum going in the opposite direction, to the left. We're going to draw it as a bigger arrow because it is negative 40 kilogram meters per second. We give that a yellow. So in order for this to happen, when you have two momentums that are adding together but they're going in opposite directions, they are going to take away from each other, because just like with every other vector, we add them together and this direction tells us the sign. If they're going in opposite directions, they subtract from each other. If they're going in the same direction, they are additive. They just add together. So in this case, we would have 20 plus negative 40, because our momentum total is equal to the sum of our different momentums. So in this case, momentum 1 plus momentum 2. So we end up with 20 plus negative 40, and our units are kilogram meters per second. I forgot to write it for this one. All right? We end up with negative 20 kilogram meters per second as our momentum total. And this is because momentum, whenever we add them all up, the sign determines the total momentum there. Okay, so in the case of above, we're just talking about one consistent, constant momentum, right? But momentum for something can change over time. And typically there's one main reason for that, and we'll notice when we look at it. So if we have a momentum, we're going to draw a line here. Move down. If we have a change in momentum, and this has a special name, it is called impulse. Right? Change in momentum is going to be equal to m and velocity. We know mass and velocity are what determine momentum. Now, typically if you're watching an object go down the road, such as like a car, can the mass just spontaneously change? No, not really. The mass of that car is the mass of that car unless you cut it in half or someone jumps on top of it while it's driving down the road. But what can change though, and what can change very easily, is the velocity. We can have a change in velocity. Now, when that happens, a change in velocity means that there has to have been an acceleration. If there's an acceleration, that means that there has to have been a net force. And so we can relate these two things in the fact that we know force is equal to mass times acceleration. Now, acceleration is equal to velocity or change in velocity over time. So we know force is equal to mass times change in velocity over the change in time. And when you look at that, this part of the equation right here is the same as what we know the change in momentum is equal to. So we can actually tie these two equations together, and we know that the net force acting on something is equal to the change in momentum over the change in time. Or if we rearrange this because we want to find change in momentum typically, or our impulse as it's called, we multiply by change in time on both sides, and we end up finding out that the change in momentum, or impulse, is equal to your F net times the change in time. Right? And a lot of times how you'll see it is impulse is equal to F delta T, or you could say that impulse is fat. Recording. So with this, remember that force is measured in newtons, time is measured in seconds, and this actually gives us our unit for momentum, which is or impulse, which is newton seconds. Now, impulse is different than momentum, and that's because impulse is only the change in momentum. Change in momentum. Right? It is absolutely not equal to momentum. Because the impulse just tells us how much the momentum changed by, not how much momentum something has. And a way that we can think of that is just like thinking about a bank account. If I tell you that you gained $500 this month, right? Does that tell me how much money I had in my account? No. That just tells me that I had $500 more than I had at the beginning of the month. But if I told you that you had $4 in your bank account, that specifically tells me how much money is in your bank account. And the same thing with momentum and impulse. Momentum tells us specifically the momentum of that object or whatever system we're looking at. The impulse tells us what the change in that momentum was. The next thing I just want to point out real quick is notice how with this equation right here, we know that change in momentum is equal to two things. We know it's equal to F delta T. We also know it's equal to mass times change in velocity. In any type of problem, you can relate these two things to each other because we can substitute these. So we could say that M delta V, let me rewrite that, that looks weird. M delta V is equal to F delta T, right? So mav fat, I guess, is what it kind of looks like. We're getting to the point where physics is more letters than numbers. Just kidding, we've already been there. Now, the last thing we're going to talk about today for our notes is going to be a law of conservation. Lost my train of thought there for a second. Law of conservation of momentum. Running out of room. Oh, there it is. Made it. So we've talked about the law of conservation of matter in here, which is matter cannot be created or destroyed in a chemical or physical change. And there's also the law of energy, conservation of energy we'll talk about. But the law of conservation of momentum tells us two things. First off, whatever momentum we start with is what we have to end up with. And then we can also rearrange this to the idea that whatever momentum occurs in situation A, the opposite has to be occurring as well on something else in order for it to cancel out. So what I mean by that is, and you guys can think about this with the little blue cart buggies we did yesterday, right? If I have student A sitting, I don't know how to draw someone sitting on a crisscross applesauce, so I'll draw them standing. Student A standing on this one, hands out. Student B is standing on this one, hands out. They need to be closer together. So student A and student B are next to each other. Neither of them is moving initially. We need some wheels on our carts. And student A and B push off of each other. Now, even if just one of the students pushed off, what's going to happen is they're both going to push away from each other with a velocity going outwards. Now, this is because of the fact that Newton's third law, action-reaction, they're both going to have the same amount of force applied over the same amount of time. And we can relate that to the fact that the change in momentum is equal to the force applied and the time at which it applied. So this gives us the amount of momentum that both students are going to feel, right? Or both students are going to gain. Now, the change of what happens with that depends on the mass of those two systems. And we saw this yesterday. If student B was 200 kilograms and student A was only 100 kilograms, that means that student A is going to have a velocity of twice of whatever B has. And then B would have a velocity of just whatever it is, their initial velocity. And this is because they had double the amount of mass, so they're going to have half the velocity, but their momentums are going to be the same, just opposite directions. This is why the student's going to be pushed out in this direction, and this one will be pushed out in the other direction. And those two momentums, because they're going in opposite directions with their velocities, they're going to be opposite signs, but equal, so when they cancel out, they're going to cancel out to zero, right? So there should be no change in momentum from what there was initially. The net momentum overall is going to end up being zero. And we're going to stop the recording right now.